In this video, I'm going to show you how we can use average bond enthalpies to calculate the enthalpy change of a reaction. Now, as I'm sure we're all aware, reactions are either exothermic or endothermic, and the heat that's transferred during a chemical reaction, either to or from the system into the surroundings, out of the surroundings, is a result of bond breaking and bond making. And to start with, we're going to show this just very simply on an enthalpy level or enthalpy profile diagram. The reaction I have in mind is the combustion of methane, so CH4 reacting with oxygen, some reaction we should all be familiar with, to form carbon dioxide and water. And the enthalpy change for this reaction is minus 890 kilojoules per mole. It's an exceedingly exothermic reaction, which means the energy is being moved from the system into the surroundings, and the temperature of the surroundings goes up. In terms of showing this on an enthalpy level diagram, we might have our reactants here, so CH4 gas plus 2O2 gas, and our products down here. So we've got, I'm going to squeeze this in here, carbon dioxide and water. Now, methane doesn't just turn itself into carbon dioxide and water in the presence of oxygen. We have to light the gas. We have to provide some activation energy. So we can see that we've got to put energy in to kickstart the reaction. And the amount of energy we put in is the activation energy, or activation enthalpy, so EA. A couple of things that I would like to point out when we're drawing enthalpy level diagrams or enthalpy profile diagrams at A level. You're often asked to sketch one. You need to make sure that your arrow for activation enthalpy firstly goes up. We don't want to see a double-headed arrow. It's not an energy transfer going both ways. And that it actually runs directly from the line of your reactants to the top of your curve. Similarly, if I was going to indicate the enthalpy change is a one-way arrow, and it runs directly from the reactant line to the product line. So this would be delta RH, enthalpy change of reaction. So a couple of common mistakes there when people are in a hurry. This is very simple to draw out, and yet they don't get the marks. So let's break this down a little. How do we actually get from methane and oxygen to carbon dioxide and water? Well, clearly what I have to do is break the bonds in the methane. So I need to break up these carbon-hydrogen bonds. And remember, a bond is in its simplest form an electrostatic attraction between the protons in each nuclei and the shared pair of electrons. So to overcome that attraction, we have to put energy in. Bond breaking is an endothermic process. When I make new bonds in the products, so for example, when I make my hydrogen-oxygen bonds, energy is released. So in an exothermic reaction, what we're saying is that more energy is released making the bonds in the products than would is used to break up the bonds in the reactants. For an endothermic reaction, we have the opposite going on. So for example, calcium carbonate, thermal decomposition of calcium carbonate to form calcium oxide and carbon dioxide. This is a reaction that requires constant heating. I've drawn that too high. I always do that. So let's put our calcium carbonate down here. It requires constant heating to form the products. So this would be my calcium oxide and my carbon dioxide. Once again, activation enthalpy runs from my reactant level all the way to the top of my curve. So that is EA. And it's an endothermic reaction, so delta RH would be labelled as such. And as we can see, my lines are exact and that's really, really important. So in an endothermic reaction, we have put in more energy to break up the bonds in calcium carbonate in our reactant than was released in making the bonds in the products. And this energy has come from the surroundings. Energy is moving from the surroundings into the system. Now, we can measure the amount of energy it takes to break a bond, let's say, for example, the carbon-hydrogen bond in methane, and this is known as the bond enthalpy or bond dissociation enthalpy. And as you can see here, it's the enthalpy change per mole when a particular chemical bond is broken under standard conditions in the gas phase. And this we will come back to, that is important. We're talking always about the amount of energy it takes to break a bond. So bond enthalpies are always going to be endothermic or positive values. Now, in terms of calculations, we're going to work with average bond enthalpies because if we can imagine methane, if I break my carbon-hydrogen bond to form CH3 in the gaseous phase plus a hydrogen, breaking that bond has been found to be 439 kilojoules per mole. And yet, if I pluck off the next couple of hydrogens, so I'm left with a carbon HCH, and then I break this carbon-hydrogen bond to form carbon in the gaseous phase and hydrogen in the gaseous phase, the amount of energy it takes to break the last carbon-hydrogen bond in methane is plus 338 kilojoules per mole. There's a difference of 100 kilojoules per mole. And that's because the energy needed to break a particular bond depends on the arrangement of electrons around this carbon atom. And this is going to change depending on how many hydrogens we've got bonded, and as they're removed, as I said, it changes. So because the actual bond enthalpy for a particular bond depends on the environment of that bond, is somehow how this is put, we work with average bond enthalpies, and the amount of energy on average to break a carbon-hydrogen bond is round about 412 kilojoules per mole. So let's finish by looking at a sample calculation. So calculating enthalpy change of reaction for the combustion of ethane. So I've got ethane reacting with oxygen to make carbon dioxide and water vapour. You'll be given the average bond enthalpy for all the relevant bonds. What you need to do to begin with is work out how many of each type of bond you are breaking and how many of each you are making. And you should do this by drawing out the molecules. People who skip this step because they think they are too good for it always go wrong. So there's ethane. I've got 3.5 oxygens. Oxygen has a double bond, and I've got 3.5 of them, and draw that like so. Those are the bonds I will be breaking. The bonds I'm making are carbon dioxide, so it's double bonds, and I've got 2 carbon dioxide and 3 waters. Now remember, water is H2O. You'd be amazed how many people write it as an H in the middle and 2 O's. Not sure why, but it seems to be quite a common error. Now, by drawing out these molecules, you can see how many bonds we are making and breaking. In the exam question, you'd be given the data for the average bond enthalpy for each bond. I'm not going to write those all down, but I can see from my molecule that I will need to break one carbon-carbon bond. 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds and 3.5 double-bonded oxygens. If I were to look up the data in the table, that would be 347 kilojoules per mole for the carbon-carbon single bond, plus 6 lots of 412 for the carbon-hydrogen bond, plus 3.5 oxygens, and each of those is 498. And if I plug that into my calculator, the total amount of energy I need to break all the bonds in the reactants comes to 4,562 kilojoules per mole. Now this is a positive value because I am breaking these bonds. I can do the same for my products. I am making 4 carbon double bond oxygens and 6 OH bonds. Quite often people won't bother drawing out the water because it's just water, and they'll put 3 OH bonds because it's 3 H2O. And it's little mistakes like that that people do under pressure and in exams when they're not thinking, or they're trying to be too clever. So I'm going to need 4 lots of 805 for my C double bond O, and 6 lots of 464 for my OH, and extend that down. When I plug that into my calculator, it comes out to be 6,004. Now, making bonds releases energy. It's exothermic, so I'm going to put a negative value in there. And then I'm just going to add those two numbers together. So, delta RH for this particular reaction is going to be plus 4562 plus minus 6004, which comes to minus 1442 kilojoules per mole. Now you'll notice here that I have not described it as the enthalpy of combustion and given it a bus stop sign under standard conditions. Why? Because in this particular reaction, I'm not working under standard conditions, because water under standard conditions would be a liquid, and in my equation it's a gas, as in the gaseous phase. So often when we use average bond enthalpies to calculate enthalpy change of reaction, it will be different, or very slightly different number compared to it maybe if we used enthalpy of formation or enthalpy of combustion data. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.